delta x. Okay, this is actually the definition of the definite integral. Okay, the idea is that we're going to be working with widths of rectangles that are getting closer and closer to 0. That's where the limit comes in. Okay, so this is equal to our definite integral. Okay, our definite integral again was from a to b of what? F of x dx. Okay, again, I'm just going back to notation. This is the accumulation function. Okay, go ahead and just integrate number 1. Again, your answer should be a number. I'm going to add a few things here. Do the answer 54? 54? Yes, no?
Yes.
Sean, do we need to? Okay, again, I give you a little box here, and I'm reviewing the formal definition, okay, because we're gonna need to make sure we recognize all that notation. So when we talk about the definite integral value of f of x with respect to x, okay, what was the actual definite integral? Okay, I give you a notation. When you integrate a function, you change it to a capital letter. Okay, so this would be capital F of x. And we would integrate that from a to b. Okay, you can either use brackets or you can use a line. Again, what did this equal? You put which limit in first?
B.
B. So it'd be capital F of b minus, pop in the lower limit, and subtract. Okay, so it's the upper limit plugged in minus the value of the lower limit plugged in. Okay, now this, when we're working with this is always going to have to be true. F is going to have to be continuous, along that function, or along the interval. Okay, because we're going to go to the average value theorem at the end of the notes today. We're assuming that the function is continuous on the interval from a to b. Okay, and that becomes important when we get to what's called average value. Okay, now take a look at the next bullet point. Okay, we've got the integration of a to b of f of x is equal to the opposite of b to a of f of x. Okay, in other words, you can swap, I like that word, because we don't use that very often in our language, but you can swap the limits. Just pop a negative out front. Pop a negative out front. When's the last time you
About mom and negative.
Okay?
Seriously?
So again, definite integral, you're talking about a number answer, okay? This is one of the properties of integrals. The value of the function from a to b would equal the opposite of the value of b to a. Swap, okay?
That's good.
And it kind of looks weird. We're going to look at it visually in a moment, okay? And then the other one is a property, okay? The value or the area under the curve, or again, accumulation function, if the limit numbers match, the area under the curve would be 0. And that should kind of make sense because you're really not going anywhere, okay? So if the upper and lower limits are the same, if the upper and lower limits are the same, the definite integral is 0. Now, you might look at that and go, well, duh. I just want to show you type of problems you might see that. Okay. So it's okay, so you can actually have more than one answer. Okay, how many of you kind of are visual people? Visual? I'm a very visual person, and it actually has to go through my fingers before I can process it. Some people are not visual, and they can just go right to the answer. You can kind of take your pick, okay? But as we go through these next problems, I'm just gonna kind of visualize it out and write it out, because it helps me. Okay, so let's take a look at number 2. You might already have the answer. Okay, obviously we don't have any functions defined. Okay, so we're looking at definite interval value of 1 to 10 of f of x, and then we're adding the definite interval value of 10 to 12 of f of x. Our answer is going to be another definite interval. Anybody have the answer just off the top of their head? Okay, Hunter, what do you got?
Capital F of 12 minus capital F of 1.
Nope, we're not evaluating it.
Oh, great.
Our answer is just another integral. Okay, so your answer in this case would be the definite integral from 1 to 12 of f of x dx. Okay, but that's again where I'm just going to kind of visualize. I like to draw it visually. Okay, so when I approach these problems, I just kind of think of a random function. It doesn't even really matter what it looks like. So I'm just going to sketch this random function. And we're talking about definite area, we're talking about area under the curve. Okay, so this first integral, I'm looking at the area under the curve from 1 until what value?
10.
10. Okay, so I've accumulated that much area. And I'm going to add on to that the value of the area under the curve from 10 to 12. So I'm talking about the overall area from what to what?
1 to 12.
1 to 12. Okay, so again, you might not need the visual, you can get the same answer without the visual. But that's the idea, you're accumulating area. Okay? Let's see if we can come up with number 3. We're looking at accumulating the area under the curve from 10 to 2. And we're going to add on to that the area from 13 to 10.
2 to 13.
10 to 2, 13 to 10. You can actually have more than one answer, by the way.
2 to 13.
Okay, so again, if it helps you, you can visualize it. I'm gonna visualize it, okay, because direction matters. So we're going from 2. I'm sorry, we're going from 10 to 2. We're going in this direction. Okay, and then we're going to add on to that 13 to 10 in this direction. Anybody got an answer for me?
So 13 to 2.
13 to
2.
13 to 2. Okay, or an equivalent answer. Swap the
Negative
limits
2 to
and put a negative out front, or you can give the answer of the opposite of what to what. Swap the limits.
2 to
2 to 13.
Don't forget the dx like I did. Okay. Make sense? You're accumulating area under the curve. Okay. Number 4, let me see what you do on your own. Working with area under the curve from 6 to 2, and adding the area under the curve from negative 4 to 6. So we got from 6 to 2, and then we're adding on from negative 4 to 6. What happens with this overlap there?
It's
Yeah, you're going to be working with adding the values and subtracting the same value. Okay, so what's your answer or answers? Is it 2 to negative 4 or negative 4 to 2?
negative 4 to 2.
Yeah, for this direction. Okay, so you give an answer of negative 4 to 2 of f of x dx, or it's an alternative answer.
Negative 2.
Opposite of 2 to
2
negative
negative
4 of f of x with respect to that. Okay, questions? Okay, let's have some fun with absolute value.
How many more pages to do? You have to be today?
With absolute value,
I think because we're reviewing
We're
this.
finishing this all the way?
Yeah, I think
It's
so.
the plan.
So we have 3 more pages?
Actually,
That's just your
if
standard
you're,
style
I think the
classical.
geometric approach is easier. You can do it geometrically or non-geometrically. We'll look at both ways. Okay, hopefully at the very least, we should all be able to sketch the graph of the absolute value of x minus 3 in the space provided. You need to just
I don't
plug in
remember.
points and get inputs and outputs and knock yourself out, but you should be able to graph that. Let's just look at it visually.
I think it's this one. I can't. Oh, okay, I did it right. Oh, sure.
Absolute value V-shaped, okay, when we're working with a definite interval value or the area under the curve from the region from -2 to 4. Okay. Now, you can actually split this as actually technically a piecewise defined function, so we can integrate the two parts separately and add them together. Okay, but you can also take what's called a geometric approach. In some cases, you could do them both ways. In some cases, you have to use a geometric approach. So I will walk you through both of those, okay? Why do you think I would say that this would be a geometric approach? What's the shape of both of the regions there? Triangles, okay? So all we simply do is find the area of each triangle and add them together. Again, you want to communicate so somebody else is reading your work and understand what they're doing, okay? So you should probably give those regions labels, okay? Give those regions labels. And just, you could use letters, you can use numbers, but I'm going to simply call this region A. And I'm going to call this little baby triangle over here region B. Okay? So let's find the area of triangle A. Okay, the area of triangle A. Okay, what form are you going to use for area of a triangle?
Base height.
1/2 base times height. Okay, so in this case, it would be 1/2 times what? Distance from here to here.
5 times 5.
Okay, what's the area of triangle A?
25 halves.
25/2. Area of triangle B? 1/2 base times height? Base of? Height of? So what's the area of B? Okay, so then, add those two together, the definite integral value from -2 to 4 of the absolute value of x minus 3 with respect to x would be the sum of 25 halves plus 1/2, which gives us an answer of 13. Okay. It's pretty easy, breezy, because when you're working with absolute value, you're going to have two triangular regions. Okay. Now, if you don't prefer the geometric approach, okay, we can actually rewrite this as a piecewise defined function. We have two separate lines.